Hi, this is Chris, and we are taking a look at a physics question here. And as we look at this question, we can see that this question is pretty elaborate. So we're probably going to break this up into several smaller videos to look at the individual pieces, but let's go ahead and read through the question. So it says, design a bungee jump apparatus for adults. Bungee jumper falls from a high platform with two elastic cords tied to the ankles. The jumper falls freely for a while the cords are slack. Then the jumper falls an additional distance with the cords increasingly tense. Assume that you have cords that are 13 meters long and that the cords stretch in the jump to an additional 22 meters for a jumper whose mass is 120 kilograms, which is the heaviest adult you allow to use your bungee jump. Heavier customers would hit the ground, which would not be good. Okay, so it says for A, will help you a great deal in your analysis to make a series of 5 simple diagrams like a comic strip showing the platform, jumper, and the two cords at the following times in the fall. And the rebound, and it says for number 1 that this is shown here as an example to get you started. So while the cords are slack. So this is kind of diagram number 1. So we'll base it off of that, and I'll do my best to kind of squeeze those in over here on the edge. So for diagram 2, it says when the two cords are just starting to stretch. So that would be, again, maybe a little further down. So our jumper, and pardon my artistic skills here, so I can help answer a physics question, but when it comes to art, skills are a little weak, so bear with me there. But basically here, the cords are still two cords that would now be attached to the feet, and there it says just starting to stretch. So that means that since the cords are 13 meters long, that here at that stage, the cords would be 13 meters. So you've still got your mg, right? And we know m is 120 kilograms. And then our cords are just starting to stretch. So this distance here at the start of diagram 2 would be a total of 13 meters when they start to stretch. And then when they are half stretched, so for diagram 3, so here we're going to start to stretch, and I'm going to just use dots to show, so after the stretch. So our jumper is still falling a little bit further, and it's going to be the same scenario here. So you've got your cord stretched a little bit further. You've still got your mg, pulling down. And instead of trying to draw stick figures all the way down, I'm just going to display it with an arrow here. But for 3, we're now going to have halfway stretch. So it would be 13, and then this would be another 11, because it says that they stretch an additional 22 meters. So this would be 11 meters of additional stretch here when they're halfway. And we can check that off. And then for 4, when the two cords are fully stretched, so that means, again, I'm going to display it with just a little bit of a dashed line, but we keep falling, and it's still a force of mg pulling us down, but now the cords are fully stretched. So this would be, another 11, which would be a total stretch, right, of 22 meters. That's the additional stretch plus the length of the cord. So we can see here that in total from our platform for those first 4, that would be a total of 13 and 22, which is 35 meters below the platform when they're fully stretched. And then for 5, I'll color code this a little bit. Let's go the opposite direction when the two cords are half stretched again on the way up. So now this would be half stretched, which would be for 5. We're on the way back up now, and we're here at this point. So on the way up, and those cords are half stretched, so that's what we would see with number 5. So the red just indicates that we've reached our max, and now we're on the way back up. So here we see mg included, and that's great. And before we even worry about any calculations or anything, let's see if we could figure out what forces might be acting at other points. So here, as we're falling when they're slack, originally we just have mg pulling down. We don't have any forces pulling up from the bungee cords, from the springs. But then here, starting at 2, so as we pass through that fully stretched point, so now as we move into diagrams 3 and 4, As those cords start to stretch, we're going to have an mg pulling down, but then we're going to start to have a spring force pulling up, and that'll be an opposing force of negative kx. So it's basically your spring constant times your displacement. And so that'll be opposing that mg at each stage. And obviously the values will change a little bit depending on, the spring constant's not changing because it's still the same spring, still the same cords, but you're going to have these different kx's depending on that displacement. So as you go further down, then you're going to have an increasing force on that spring pulling you back up more and more until you come to a stop and then start to spring back up in your bungee journey in this problem. So that's what we have here as far as a setup on this. And now up next, we're going to get into answering some of those questions that require maybe some calculations. But, we'll see samples of those here in B. At what instant is there the greatest tension in the cords? What's the jumper speed at this instant? Which of the following statements is valid basis for answering part D directly? And, a lot of these are going to be conceptual. And then down here, we're going to get into some more numerical calculations. So we're going to tackle those in a separate video, just to break these up a little bit, because this is a really big, elaborate problem. So that's the situation, and that's part A with a few different diagrams displaying the different phases in our bungee jump. And now we're going to get into looking at this both conceptually and numerically coming up.